Now that you're becoming more comfortable, hopefully, with using the fundamental theorem of calculus, we're actually going to use the fundamental theorem of calculus in problems. So at the end of this lesson, you'll be able to use the fundamental theorem of calculus to analyze graphs. All right, you'll notice, let me just go ahead and read the problem. The graph of f shown consists of a semicircle and two line segments, as you can see, on the interval from -2 to 6. In example 1, it's letting us know that g of x is equal to the integral from 2 to x of f of t, and it says to use the graph of f to do the following. We're going to answer lots of questions about this specific graph, and the biggest thing is, just remember before when we had problems like this, when we made our f prime and our f double prime chart, it kind of made the problem a lot easier to work. Kind of the same thing with these problems. We're going to go ahead and figure out what this graph is telling us about information and then see if we can figure it out. Okay, this is the graph of f right here. It's letting us know that g is equal to the integral of f. So if we have a picture of f and it asks us to find the integral, what we're going to be looking for is the area under the curve. Okay, another thing I'm sure it will be asking us about in one of the other parts is going to be g prime. And when I'm looking at g prime, remember, if this is g, if I took the derivative of both sides, what's going to happen when I take the derivative of an integral? The derivative and the integral are going to just cancel out, so I'll just be left with f. And f, this is a picture of f, so we're just going to actually look at the curve. Okay, and then there will be asking me some questions about g double prime. Well, if g prime is equal to f, then g double prime, if I take the derivative again, it's going to equal f prime. So we're going to be looking, if this is f, or this is a curve, we'll be looking at f prime, so we're going to be looking at the slopes. And so if we can just remember, usually what I do on these problems, I always write this down first, and then I think it saves me a lot of time as I'm actually going through the problem. All right, so this one asks us to calculate g of -2, and I've already noticed up here we're going to be looking for an area under the curve. Well, we're letting our x value be -2, so I'm going to actually rewrite this problem. It tells us that g of -2, it's actually going to equal the area under the curve from 2 to -2 of f. So we're going to use this picture and we're going to find the area between 2 and -2. But if you remember, we're not allowed to go from a higher number to a smaller number, so I'm actually going to bump that around. It's just going to be the opposite of whatever I get when I go from -2 to +2. Okay, from -2 to +2, I notice that that's a half circle, so we'll have negative from that negative over there. Half circle will be 1/2 pi times the radius squared. The radius is going to be 2. And so when I calculate that out, 2 squared is 4, times 1/2 is 2, I'll end up getting -2 pi. All right, the next one, it says g of 0. So this one, we're going to calculate the area under the curve from 2 to 0 of f. And again, we're not allowed to go from a bigger number to a smaller number, so it's going to be the opposite of what I get when I go from 0 to 2. Okay, so when I go from 0 to 2, I notice this time it's just a quarter circle, and I'm going to put that negative out front just from this part of the problem, so 1/4 pi, the radius is still 2, and when I work that out, I'll get -pi. Okay, the next one is g of 4. So when I calculate g of 4, again, I'm going 2, and I'm putting in my x is 4, so 2 to 4 of f. So this is asking me to find the area under the curve from 2 to 4, and I believe that looks like a triangle, so it's going to be 1/2 times the base. The base of that triangle will be 2. The height of that triangle will be 4, and so that answer will be 4. And then the last one, it says to do g of 6. So that's going to be the area under the curve from 2 to 6 of f. So if I look at from 2 to 6, 2 to 6 is actually going to be a triangle and another triangle. So this first triangle, I'm going to do 1/2. The base of that triangle, it goes from 2 to 5, so that base will be 3, and the height will be 4. And so that one will be 6. And then the second triangle is going to be 1/2. The height will just be, or the base will just be 1, and the height goes down to -4, so I'll put 4. So that will be 2, but since it's below the x-axis, it will be -2. So when I add those two together, I will get 4. So that's how you calculate it if it's just asking you for g. Okay, second part, same picture. Again, I'm just going to write up here that g was the area under the curve, g prime was f, or just the curve, and then g double prime was f prime, or the slopes, because we're looking at the derivatives. Okay, so this one, it's asking us to find g prime of everything. So I'm going to go up here. G prime is just the curve. So what's happening on the curve? So when I'm finding g prime of -2, I'm actually just looking at what's happening on the function at -2. So if I go to -2, what's happening is the y value there is 0. Okay, and if I'm finding g prime of 0, that's really just f of 0. So at 0, my function is at 2. Then g prime of 2 is the same thing as f of 2. And if I look at 2, that y value is just 0. And then g prime of 4 is the same thing as f of 4. So if I just look at 4, it looks like it's up at 4. And then g prime of 6, if I go over to 6, it's going to be the same as f of 6, and that function is at -4 right there. So that's all you have to do for that specific part. Okay, next part. It's asking us to find the intervals on which g is decreasing, concave up, points of inflection. So we know that increasing and decreasing have to do with g prime. Concavity has to do with g double prime, and points of inflection have to do with g double prime. Well, I'm just going to write up here again. We found g prime, that we are just looking at f, or we're just looking at the curve. And then g double prime, we're looking at f prime, or the slopes. Okay, so for part C, the first thing that I'm going to do is make myself a g prime chart. Okay, if I'm looking for a g prime chart, it's just the same as the f chart. So I'm going to look at, remember, we're going to find where this equals 0. So we're going to look at where does f equal 0. That would be at 2 and at 5. And I'm just ignoring over here because that's the endpoint of our interval. So to the left of 2, notice that g prime or f is just above the x-axis. And then between 2 and 5, it's still above the x-axis. And then from 5 to 6, it's below the x-axis. So when this says where is g decreasing, it's going to decrease from 5 to the end of the interval, which is 6. And that is because g prime is negative. So still same explanations that we'll use from problems from the last chapter. Okay, D and E are talking about concavity, so I am going to talk about g double prime this time. So I would like a g double prime chart. Remember, g double prime is the same thing as f prime, so the slopes of these. So the slopes are positive until I get to x equals 0. The slopes are then negative till I get to x equals 2. The slopes are positive till I get to x equals 4. The slopes are negative all the time after that. Okay, then from here, when it's asking for where's g concave up, we just look at where the second derivative is positive. So I would say from -2 to 0 and from 2 to 4. And that's because g double prime is positive. And then the x-coordinates of each point of inflection, as long as g double prime changes sign, it changes sign at 0, 2, and 4. So I could say x equals 0, 2, and 4 are points of inflection. And that's because g double prime changes sign. All right, let's try one more part. This one is asking me to find the absolute extrema of g. If you recall, when we're looking for absolute extrema, we're actually going to find the critical number. So we're going to find where g prime equals 0, and then we actually have to evaluate the numbers at the different endpoints. So let's go ahead and figure out where does g prime equal 0 first of all. We actually already found out where g prime is equal to 0, and I'm just going to go back here. We found out that g prime was equal to 0 at 2 and at 5. So I'm going to go ahead and put 2 and 5 are our critical numbers. So now what we're going to do, we need to find g of 2, we need to find g of 5, and then we also need to find the values at the endpoints. We need to find g of -2, and we need to find g of 6. And whichever one of those gives us the highest value and the lowest value, we will have found the extrema. So first thing that we want to do is calculate g of 2, which again, going back to the first slide that we did, part A, I would like to find the area under the curve from 2 to 2 of f. Well, you can't go from 2 to 2 because you're not going to cover any distance, so that one will equal 0. This next one, we're going to go from 2 to 5 because that's where the x value is. So if I'm going from 2 to 5, notice it's a triangle, which is going to be 1/2. The base of that triangle will be 3. The height of that triangle will be 4. So this one will give me a value of 6. Okay, from -2, we'll do 2 to negative 2, and we actually calculated that on the part A, so I'm just going to write down that when we did that we got negative 2 pi. And then g of 6, I believe we already did that also. When we calculated g of 6, we got 4, and that was again from part A. So if I'm looking for an absolute extrema, the absolute min, the lowest value that the function is ever going to reach is this negative value, so my absolute min will be negative 2 pi. And then my absolute max, the highest number that I'll ever get on this function, was 6. So we have now found the absolute extrema. So hopefully now you can analyze graphs using the fundamental theorem of calculus.